Alright, so Tony just talked to you guys about position, velocity, position versus time graphs, and velocity versus time graphs. So what I'm going to be teaching you guys today is the next step in that cycle, and it's the acceleration and acceleration versus time graphs. But before we start, we're going to do a little bit of practice on what we learned with Tony already. So a car is moving along a straight road. The graph below shows the car's position versus time graph. At what point or points do the following conditions apply? The displacement is 0, the speed is 0, the speed is increasing, the speed is decreasing. So we know that displacement is equal to delta x, which can also be rewritten as x final minus x initial. Well, this is going to have to be 0 because that displacement is 0. We can figure out the x initial position by looking at what the position is whenever time is equal to 0. This is 0 meters, so we can replace this also with 0. So really, we're looking for whenever x final is equal to 0. In this case, only d is the point wherever the displacement is equal to 0. So d is the only one. The speed is 0. Now what we learned with Tony is that the speed of a position versus time graph is the slope. So we get delta x over delta t is going to be equal to v, which is the speed. Okay. Well, we know that this delta v is going to be equal to 0, so we can just replace this with a 0 real quick. Okay. Delta t can never be 0 because it's going to be a change in time. You can never have 0 change in time. It doesn't make sense. So really, you're looking for whenever delta x is equal to 0. This means that the initial and the final positions are going to be the exact same. What this means is that on the position versus time graph, it's going to be a horizontal line or a slope of 0, which is the point of the speed is 0. So this is the only point is going to be E, and it's going to be point B. Sorry, that's not straight, but no. So point B and point E. Okay, the speed is increasing, and then we have the speed is decreasing. Okay, well, we know that the speed is a slope of this, so we can really write the slope is increasing, the slope is decreasing. Okay, now let's think about this. A slope increasing means it's getting steeper. A slope decreasing means it's getting less steep. Okay, well, let's look at point A. Well, we see that at point A, or before point A, it's at a slope around right here. When it gets to point A, it's going to get a little bit smaller to the point where it's going to get to 0 at B. So from transitioning from the initial to B, you're going to start slowing down. The slope is getting less steep, meaning it's decreasing. So we have point A. Meanwhile, at C, we have 0, we have a slope of 0, and then we're getting some positive slope. So from here to here, we're going to see it increasing, which means that point C is going to be decreasing. Now, although D looks like it could be also increasing, I tried my best to make this a straight constant line. So before D and after D, it's not increasing nor decreasing. So it can't be really placed anywhere. It can't be placed under the speed is increasing or the speed is decreasing. So that's like a review of what Tony did with you guys. If you have questions, you can just go back to the video. Maybe he answered it, or you can just ask us directly. Alright, so now it's time to get to the new stuff, the fun stuff. Yay! Alright, acceleration. Acceleration is the rate of change of velocity. You can also see this as velocity is the rate of change of position. So the same way that velocity is the rate of change of position, you can think of acceleration as the next step, except this time it's the rate of change of velocity. So instead of this, delta x over delta t, you're going to have now delta v over delta t, which can also be rewritten as velocity final minus velocity initial over the change in time, which is the final time minus the initial time. Now, if you want to figure out the units of acceleration, well, you know that velocity is going to be meters per second. Time is going to be in seconds. Meters per second divided by the second is going to be meters per second squared. Or you can write it as meters per second. Both of these are correct ways to write acceleration, but later on, whenever you get to more complicated units and trying to plug stuff in for acceleration, you're going to want to, it's going to be easier to write this than trying to learn how to write this, because this starts to get a little bit complicated, and you're going to end up just wanting to write this because this makes everything so much faster. Also, normal people write this, and weird people write this. So if you want to be normal, then go ahead and just write meters per second squared. Alright, this, as in the acceleration, can only tell us how the velocity is changing. Acceleration cannot give what the velocity of an object is. Now, this is an important concept of acceleration. The acceleration is only describing how the velocity is changing. As you see here, the acceleration is only describing how the velocity is changing over the time interval. You can't tell what the velocity of an object is. You can only tell by how much it's changed by. It could start off with 1 and it changes by 4, leaving you with 5. Or it could start off with 3 and it still changes by the same 4, but it ends up in 7. You can't figure out how much what the velocity of the object is unless you're given that information directly. Then you can somehow figure it out. This is, again, an important concept that you have to know, and I'll explain it a little bit better later on when we get to the graphs, but just this is one of the things that the College Board always tends to trick people on. So make sure you remember that note. Alright, let's do a quick example. It takes 9 seconds for a Chevy Sonic to go from 0 meters per second to 27 meters per second. What is the acceleration of a Chevy Sonic over the 9-second period? Okay, acceleration equals delta V over delta T. Also be written as V final, V initial over T final minus T initial. Well, it's going from 0 to 27, so this is the final, this is the initial. So 27 meters per second minus 0 meters per second over the 9-second period. So really it did the math for us, so we don't have to bother, just 9 seconds. 27 meters per second over 9 seconds is going to leave you with 3 meters per second squared, or meters per second, but I again want to just state that you might want to get used to writing meters per second squared because it just makes life easier later on. Alright, graphs. An object's acceleration is the slope of the velocity versus time graph. You can also see this by an object's velocity is the slope of its position versus time graph. So we know that acceleration is equal to delta V over delta T. Well, if we look at this graph and we were to do the rise over the run, from 2 to 3 seconds, you see that the delta V is equal to 3 meters per second, and then the delta T is equal to 1 second. So then you get 3 meters per second over 1 second. This gives you the 3 meters per second squared we got earlier. Now, some people get confused by defining, okay, the slope of what is what now? So an easy way to do it is a little trick, is you look at the units of what is plotted on the y and the x. So if you wanted to find this, if you were going to find the acceleration, then you would look at this and see if you have to divide or multiply these two. If you divide meters per second divided by second, you get that meters per second squared. That gives you the acceleration. So you know that rise over run will give you the slope. You can also think of this as trying to find the displacement. If you were to do meters per second times second, seconds cancel out, you get the meters, which is the displacement of a velocity versus time graph. So you can see that just by doing that step, you can figure it out what you're trying to look for by looking at the units. So it can really help you out if you just get confused or just forget sometimes. So just make sure you know what the units of velocity, time, position, and acceleration are, so you can figure out which one you're trying to find. Alright, next step. Alright, we're going to split this up into 3 parts right here, and this is the corresponding acceleration versus time graph. Okay, so for part 1, we're going to need to find the acceleration, which we know is going to be 2, but we can calculate it from here. It's going to be the delta V over delta T, which is going to be this increase by 2 meters per second over 1 second. So increase by 2 meters per second, and this is 1 second time interval, so it's going to be 2 meters per second squared. And this 2 meters per second squared is going to last for 1 second, so that's why it's here. This is acceleration, which is 2 meters per second squared, and it lasts for exactly 1 second. Alright, the second part. Acceleration, again, delta V over delta T is going to be equal to the change in V. Well, here it's staying at 2 from the beginning to the end. So really, there's no change in in V. Change in T, however, is 2 seconds. Still, either way, it's going to be 0 meters per second squared. 0, not whatever that was. 0 meters per second squared. All right, well, this 0 meters per second squared lasts for 2 seconds. So we graph it here. 0 meters per second squared, 2 seconds. Final part. Okay, acceleration is equal to delta v over delta t. All right. The final velocity is going to be 0. The initial velocity is 2. So really, this is 0 meters per second minus 2 meters per second over, and then 2 second time interval, 2 seconds. This is negative 2 meters per second over 2 seconds, negative 1 meters per second squared. This negative 1 meters per second squared lasts for 2 seconds, negative 1. Now, if you've noticed, a positive slope on the velocity versus time graph, positive acceleration. 0 slope velocity versus time graph, 0 acceleration. Negative slope velocity versus time graph, negative acceleration. This is the same thing as whenever you're going from position versus time to velocity versus time. You see here, positive, positive, 0, 0, negative, negative. Time intervals vary, but still, you can figure it out. You can also convert from acceleration versus time back to velocity versus time, which is the same ideal properties of whenever you're going from velocity versus time to position versus time. But we don't have to worry about that right now because we'll do it later on. So you worry about that later. Just be prepared. Alright, acceleration is a vector. Then, since velocity is a vector and is used to calculate acceleration, so acceleration is equal to delta v over delta t. Acceleration must also be a vector. Well, vector, vector. Yeah, it makes sense. That's how it works. If acceleration points in the same direction as velocity, the object is speeding up. If acceleration points in the opposite direction as velocity, the object is slowing down. What I tend to remember about this is that if the v vector is described as pointing to the right, and the acceleration vector is described as pointing to the right, they're buddies. They're helping each other out. So that means for every second that passes, the v is going to increase to the right by this much. It's speeding up in the right direction. However, it can also speed up in the left direction. So if we were to take a different scenario where the v vector is actually pointing to the left, but the acceleration vector is also pointing to the left, they're still buddies. Every second that passes by, the v vector is going to increase by this amount, the magnitude of this acceleration vector. However, if acceleration points in the opposite direction, the object is slowing down. Here is whenever the v vector is going to be pointing one way, and the acceleration vector is going to be pointing the opposite way. Here, they're enemies. The acceleration is going to try to push the velocity to be going back in that direction, so it could be speeding up again. So every second that passes, this velocity is going to feel a decrease by this amount because they're opposite direction. This also is true for whenever the velocity is pointing to the left side. Whenever the velocity is pointing to the left side and the acceleration is pointing to the right side, they're enemies again. The velocity is going to decrease by this amount every second. To better explain this, you can look at it this way. We just said that positive a, or in this case, in other scenarios right here, the right is positive and the left is negative. So the object is moving to the right, so that means that it has a positive velocity. The acceleration is to the right and it's positive. We just said that on a velocity versus time graph, we said it right here, a positive velocity, a positive slope, positive acceleration. So positive acceleration, positive slope on the velocity versus time graph. So it's already at a positive, so it's going to be speeding up. You see here, as time increases, the velocity also begins to increase. Now here, you can see the acceleration is pointing to the right, which means the slope has to be to the right, but the object is moving to the left, which means it's negative. Now, although you can see the slope is increasing, the velocity, however, it's slowing down. It's getting closer to zero. So if someone's running to the left at a pace of 5 miles per hour, and they begin to slow down, they're slowing down to 0. That's what you have to understand about this. Slowing down means getting closer to 0, not necessarily complete, like a positive acceleration means it's always going to be increasing, or it's always going to be speeding up. This is the complete opposite now. Negative a, negative slope. Makes sense. But since this object is moving to the right, it's going to have a positive and it's going to have a negative slope. It's going to be slowing down. It's going to be getting closer to the 0 value. This one here is going to is moving to the left and it's speeding up. Negative a, negative slope. It's getting away from 0, meaning it's speeding up but going to the left. Here, speeding up going to the right. Here, slowing down but it's still moving to the left. Here, slowing down but it's moving to the right. Slowing down, I want to say again, is getting closer to 0, not necessarily just getting away. It's just like it's getting closer to 0 basically. That's all you really have to know about. So let's do an example. If left is negative and right is positive, is the acceleration positive or negative? Well, in this case, you see acceleration is pointing to the right, so it's really just positive. That's all it asks for. It doesn't ask for anything else. All right. The particle is moving from point 1 to point 2. So the particle is this dot right here with the velocity of v1. This is right here, the vector. What is the velocity vector of the particle once it reaches point 2? So we assume that in this, it's going to take 1 second to get there because that's how a particle diagram works. Sorry. All right, let's see. These are opposite. So that means that the velocity is going to decrease by this amount. So really, it can't be a just straight off the bat because this would mean that it's increasing in this direction. Okay, how much is it going to decrease by? Well, we take this magnitude, and I'm going to try to draw it as perfectly as I can. It's going to be right here. This is the a vector again. So every second that passes by, aka from when it goes from 1 to 2, it's going to decrease by this amount. So the end vector would be velocity 2 of this magnitude, which is going to be closest to b. However, you might be wondering, how would this happen if it's c, d, or e? Well, for c, if we have this initial velocity, then the acceleration has to be the exact same, just facing the opposite way. Now what this does is for 1 second that passes by, the acceleration is going to force the velocity to change in the other direction by this amount. This means that these would cancel out, leaving behind the 0 vector. Now how about these that points in the opposite direction? Well, really, you can just think about this as just the same velocity vector, except the acceleration is so large that it'll turn the object straight around and start pushing it the other way. This means that whenever you subtract these two, you'd get a leftover velocity vector of this right here. Velocity vector of this right here for v2. Now, you still might be wondering, what about this longer one? Well, it's just going to be a longer acceleration, really. Long acceleration, whenever you subtract these two, the longer leftover v2 you have. So, but in this scenario, this acceleration is smaller than the vector, so it's not going to turn it completely around, and it's not going to be equal to 0 because these aren't the same magnitude. So the answer is B. Alright, the particle shown is slowing down. What are the signs of the position and velocity? So we know it's slowing down because the velocity and the acceleration aren't friends. The acceleration is taken away from the velocity. What are the signs of the position and the velocity? So we're going to then call the right positive, the left negative. The position is going to be, okay, well, we know the 0 is right here. 0 is right here. We know that this is greater than 0. So at the initial point, it's going to be a random positive number. And at the final point, it's still barely going to be a positive number. So really, in this entire scenario, the position is positive. Now, what about the velocity? The velocity is pointing to the left, and it's always pointing to the left. This means that the velocity is negative. Now, if it asks for the acceleration, you would say the acceleration is positive. If you didn't have this, and you only knew this, but it still said it's slowing down, you would have to know that the acceleration is going to be the opposite of the velocity because it's slowing down. They're taking away from each other. It's going to get closer to 0. Alright, a cyclist riding at 20 miles per hour sees a stop sign and comes to a complete stop in 4 seconds. He then, in 6 seconds, returns to a speed of 15 miles per hour. What is his motion diagram? Okay, let's think about this. He's riding at 20 miles per hour and comes to a complete stop in 4 seconds. Okay, this means that he's going to a complete stop. He's going to 0 miles per hour. He's slowing down. What this means is that the acceleration and the velocity for the first 4 seconds must be opposite of each other. So it can't be A because they're both facing the same way, and that wouldn't mean that it's slowing down. He would be speeding up in this case. B has them opposite, C has them opposite, and D has them facing the same way, so it also can't be D. Alright, he then, in 6 seconds, returns to a speed of 15 miles per hour. Okay, well he goes from 0 then, wow, I can't write zeros to save my life, 0 miles per hour to 15 miles per hour. This means he's going away from 0. Oh my god! Okay, he's going away from 0. He's speeding up. So this means that the velocity and acceleration must be pointing in the same direction. But both B and C have that value. The velocity and acceleration are both in the same direction. So you might be wondering, well, if they both have that, what's next? You look at the magnitude of the vectors. At first he's at 20, then he's at 15. You see the difference here is that one is larger than the other, and then the other side, one is larger than the other again. But at first, he was at the larger value, then he was at the smaller value, which shows B as the correct answer. Since C would mean that this is 15, and that's 20. B would show that this is 20, and that's 15, which makes B the right answer. Alright, what is the sign of the acceleration of the 4 motion diagrams below? So again, these particle diagrams represent the object, and then this vector is going to be the velocity. So it starts off here, and the velocity is slowly increasing all the way. It's speeding up. It's going away from that 0 value. So this means that the acceleration and the velocity must be buddies. So that means that, and if we call the right positive, the left is negative, we know that the acceleration must be facing positive. Now here we're starting from this position again. You see that the velocity vector is large, but it's slowly approaching this 0. This means that the acceleration and the velocity are not buddies. One has to be pointing away from each other. Since you can't really change this, you know that the acceleration must be pointing to the left side, meaning that it's negative. Alright, now we're starting on this side. We see a large vector which slowly is decreasing. This means that the acceleration and velocity must be pointing in opposite directions. This means that the acceleration must be pointing to the right. And since the right is positive, it's positive. It's the sign of the acceleration is positive. Now here we have again. The vector is small and it's slowly increasing. It's speeding up. It's going away from 0. So they must be pointing in the same direction. Acceleration must be also pointing to the left, just like its velocity. And since the left is negative, we have a negative sign for the acceleration. Alright, the area of an acceleration versus time graph. The same way displacement is the area of a velocity versus time graph, the change in velocity is the area of acceleration versus time graph. So the way you get delta x is for v versus t, delta v is for a versus t. Now you can see this by looking at here. Alright, so we have this value right here, 4 seconds, and then we have this 2 meters per second squared. So we're finding the area of this triangle. We know that it's going to be 1/2 base times height. Well, 1/2, the base is 4 seconds. The height is 2 meters per second squared. If you're good with math, which I don't know, I feel like you should be, at least a little bit, that you've realized that this is going to be 4. The coefficients is going to be a value of 4. However, you see that the units might trick you up a little bit. So let's do this separately. Meters per second squared times seconds. One of these seconds are going to cancel out. So you're left with meters per second. So 4 meters per second. Now again, this is the delta v. You can see this by A is equal to delta v over delta t. If you multiply delta t to both sides, you get A times delta t is equal to delta v, which is exactly what we just did here. A is 2 meters per second squared, and we multiply it by this delta t, which was 4 seconds, so we get the change in v, 4 meters per second. Oops. The slope of an acceleration versus time graph. Now you know that the slope of a position versus time graph is equal to the velocity. You know that the slope of a velocity versus time graph is equal to the acceleration. So the acceleration versus time graph, the slope of it is going to be equal to something. Slope of acceleration versus time graph is a jerk. You do not need to know this. You don't have to even write this down if you don't want to. But it's kind of cool. Just like it's kind of cool just to know it, not like kind of cool concept. So again, if you want to do it, rise, run, you get 2 meters per second squared over 4 seconds. It's going to be equal to 1/2 meters per second cubed. Or if you want to be even more weirder than before, 1/2 meters per second per second per second. I'm going to say this one more time because most of y'all are going to like try to remember this or study this, put it in your head, but you do not need to know this. You're never going to really see jerks jerks in physics. You could see some people that are jerks, but you're never going to see the term jerk in physics as a unit. It's not really necessary. It's just something you should know for fun. Alright, so important things to remember. Acceleration is the delta v over delta t, which can be rewritten also as the velocity final minus the velocity initial over the time final minus the time initial. The acceleration cannot give the velocity of an object, only the change in velocity of that object. Again, this is really important. That's probably one of the most important things that you need to know. You can only get the change in velocity from an acceleration. If you're ever asked to give the final velocity, the initial velocity, or possibly even the distance traveled when you're just given the acceleration, you're supposed to say that it's not possible. You need more information. Because unless you don't have one of those, unless you don't have the initial velocity or the final velocity, you can't really tell what it is. You only know what it's going to change in. If the acceleration is going to measures the change of velocity, and the change of velocity is 4 meters per second, and you don't know what the object's initial velocity is, then it could be 2, and then the final velocity could be 6. But if you don't know for sure, then how can you know that the final velocity will be that 6? Maybe it's 3, making that final velocity 7. Maybe it's 4, making that final velocity 8. You can't tell unless you're given more information. So again, if you're just given the acceleration and the time interval, you can only figure out what the change in velocity is. You cannot figure out what the final velocity is, the initial velocity is, or even the distance traveled by that object. If the acceleration points in the same direction as velocity, the object is speeding up. If A and V are buddies, they're going to help each other out. They're going to grow with each other. If they're enemies, they're going to take away from one another. They're going to make each other slow down, which is exactly what this does. If the acceleration points in the opposite direction as velocity, the object is slowing down. You see there that this velocity will change by this magnitude every second that passes by, leading it to slow down towards the 0 value. The area of an acceleration versus time graph is the change in velocity. The change in velocity. It's not the initial, it's not the final, or it's not even the displacement. I'm going to say it one more time. The acceleration cannot give the initial velocity, the final velocity, or the distance traveled of the objects. Alright, thanks, I guess. If you want, you can feel free to ask questions. I'll definitely get Tony to answer them, because I just don't feel like it sometimes. Sorry if my handwriting is bad. I'm doing this for y'all, so you can't really complain. Yeah. Take care.